Richard Dedekind 2870, when publication, on the theory of ideals, represents a watershed moment in the development of abstract algebra and number theory. This work transcends a mere collection of results. Instead, it presents a novel framework for understanding algebraic number fields, shifting focus from individual numbers to sets of numbers possessing particular algebraic properties. The impact of this approach resonates across mathematics, influencing fields ranging from algebraic geometry to cryptography. The genesis of Dedekind's theory originates in the challenges posed by attempts to generalize the fundamental theorem of arithmetic to algebraic number fields. This theorem, a cornerstone of elementary number theory, asserts that every integer exceeding unity can be uniquely expressed as a product of prime numbers up to the order of the factors. Early investigations into higher reciprocity laws, notably by mathematicians such as Carl Friedrich Gauss and Ernst Kummer, revealed this comforting property falters in certain algebraic number fields. In settings involving complex numbers satisfying polynomial equations with integer coefficients, unique factorization can fail. Ernst Kummer, aiming to salvage unique factorization, introduced the concept of ideal numbers. These ideal numbers, while lacking concrete existence within the initial number field, were conceived as entities that, hypothetically, restored unique factorization. Kummer made significant strides in the study of Fermat's last theorem using ideal numbers. However, his approach remained somewhat ad hoc, lacking a firm theoretical foundation. Dedekind, building upon and significantly extending Kummer's ideas, sought to provide a rigorous and intrinsic definition of these elusive ideal Dedekind's central innovation lies in replacing Kummer's ideal numbers with what are now known as ideals. An ideal within a ring constitutes a special subset closed under addition and absorption. Specifically, if two elements belong to an ideal, their sum also belongs to the ideal. Moreover, if an element belongs to an ideal, any element multiplied by something from the original ring also belongs to the ideal. This absorption property distinguishes ideals from other subsets. Dedekind demonstrated that ideals could serve as surrogates for Kummer's ideal numbers, inheriting their crucial properties while possessing a clear and well-defined existence within the number field itself. On the theory of ideals, Dedekind painstakingly develops the arithmetic of ideals. He defines operations such as ideal addition and ideal multiplication, demonstrating that ideals form an algebraic structure. Crucially, he proves a replacement to the unique factorization theorem. In the ring of integers of an algebraic number field, every ideal can be uniquely expressed as a product of prime ideals, ideals which cannot themselves be factored into smaller ideals. This theorem restores a form of unique factorization, resolving the problems that motivated Kummer's initial work. Dedekind introduced the concept of a module. A module acts as a generalization of ideals to encompass sets of numbers which are closed under addition and scalar multiplication, elements from a ring. He described the concept of the norm of an ideal. He introduced the notion of fractional ideals, which are modules that, when multiplied by an appropriate element of the ring, become ordinary ideals. These concepts were crucial for developing a comprehensive theory of algebraic numbers. The immediate impact of Dedekind's work lay in its ability to systematize and clarify existing results in algebraic number theory. Kummer's work, while insightful, suffered from a lack of conceptual clarity. Dedekind's theory provided a clean, axiomatic framework that eliminated ambiguities and facilitated further progress. Number theorists rapidly adopted Dedekind's approach. It served as the foundation for substantial advances in understanding the structure of algebraic number fields. Following Dedekind's work, mathematicians began to explore the properties of ideals in more general rings. Emmy Noether, in the early 20th century, revolutionized the field by abstracting Dedekind's ideal theory. Noether developed the concept of a Noetherian ring, a ring in which every ideal is finitely generated. Noetherian rings are characterized by the ascending chain condition on ideals. This means that any ascending sequence of ideals must eventually stabilize. Noether demonstrated that Dedekind domains, rings in which every ideal factors uniquely into prime ideals, could be characterized by simple properties. Dedekind domains are Noetherian, integrally closed, and every non-zero prime ideal is maximal. These abstract characterizations of algebraic structures proved remarkably fruitful. The theory of ideals finds applications far beyond its initial context in number theory. In algebraic geometry, ideals play a central role in defining algebraic varieties. An algebraic variety is the set of solutions to a system of polynomial equations. The set of polynomials vanishing on a given variety forms an ideal, called the ideal of the variety. The correspondence between ideals and varieties lies at the heart of algebraic geometry, allowing geometric problems to be translated into algebraic problems and vice versa. The study of singularities of algebraic varieties relies heavily on ideal theoretic techniques. The legacy of Dedekind's work also extends to modern cryptography. Ideal lattices, lattices constructed from ideals in algebraic number fields, are used in the construction of cryptographic systems. These systems resist attacks from quantum computers. The security of these systems rests on the difficulty of solving certain computational problems involving ideals, such as finding short vectors in ideal lattices. The initial reception of Dedekind's theory was mixed. Some mathematicians, accustomed to working with concrete numbers, found the abstract nature of ideals difficult to grasp. Leopold Kronecker, a contemporary of Dedekind, developed an alternative approach to algebraic number theory based on polynomial forms. Kronecker's approach, while also rigorous, was more computationally oriented and less conceptually elegant than Dedekind's. Over time, Dedekind's approach gained dominance due to its clarity, generality, and applicability to a wider range of problems. One critique of Dedekind's approach concerned its reliance on set theory, a relatively new and controversial field at the time. Some mathematicians questioned the validity of set theoretic arguments, fearing they could lead to paradoxes. Dedekind was a staunch defender of set theory, arguing for its necessity in providing a solid foundation for mathematics. He engaged in extensive correspondence with Georg Cantor, the founder of set theory, discussing the philosophical and technical aspects of the subject. Dedekind's work was directly influenced by the work of Carl Friedrich Gauss, particularly Gauss' Disquisitiones Arithmeticae. Gauss laid the foundation for modern number theory, introducing concepts such as congruences and quadratic reciprocity. Dedekind deeply studied Gauss' work, seeking to generalize its results to more general algebraic structures. He also drew inspiration from the work of Peter Gustav Lejeune Dirichlet, who applied analytic methods to the study of number theory. Dedekind attended Dirichet's lectures and edited his collected works after his passing. The influence of Dedekind's theory on subsequent mathematicians is undeniable. Emmy Noether, as mentioned earlier, played a crucial role in abstracting and generalizing Dedekind's ideas. David Hilbert, a leading mathematician of the late 19th and early 20th centuries, applied Dedekind's ideal theory to the study of algebraic number fields, proving important results on class field theory. Emil Artin further developed class field theory, using ideals to study the structure of Galois groups of algebraic extensions. The work of these mathematicians, and many others, solidified Dedekind's legacy as one of the most important figures in the history of algebra and number. Beyond the specific mathematical results, Dedekind's work exemplifies a shift in mathematical thinking towards abstraction and axiomatization. He demonstrated the power of defining mathematical objects in terms of their properties rather than their concrete representations. This approach, which became a hallmark of modern mathematics, has proven remarkably successful in unifying disparate areas of mathematics and in uncovering deep connections between seemingly unrelated concepts. Dedekind's influence extends far beyond the specific results contained in On the Theory of Ideals. It is felt in the very fabric of modern mathematical thought. The move away from concrete representations initially created some difficulty. The power of Dedekind's abstraction resides precisely in its focus on the essential properties of algebraic structures, enabling generalizations that would be difficult or impossible to achieve through more concrete approaches. This principle proves central to contemporary mathematics. The ability to appreciate essential structures underlies the progress of modern mathematical research. A subtle, yet important, aspect of Dedekind's work is his careful attention to definitions and proofs. He was meticulous in ensuring that all his arguments were rigorous and logically sound. His emphasis on rigor helped to raise the standards of mathematical proof and contributed to the development of a more precise and unambiguous mathematical language. This emphasis on rigor, sometimes perceived as excessive, reflected a deep commitment to intellectual honesty and a desire to build mathematical knowledge on a solid foundation. In conclusion, Richard Dedekind's On the Theory of Ideals stands as a landmark achievement in the history of mathematics. It provided a rigorous and conceptually elegant framework for understanding algebraic number fields, resolving long-standing problems and opening up new avenues of research. Its impact extends far beyond number theory. It has influenced algebraic geometry, cryptography, and the very foundations of modern mathematics. Dedekind's work exemplifies the power of abstraction, axiomatization, and rigorous proof in unlocking the secrets of the mathematical universe. His legacy continues to inspire mathematicians today. The ideas introduced here form the bedrock of much of modern algebra, a testament to their enduring power